Hello, and thank you for joining us again. So let's continue with our intersections of planes and our intersections of planes with lines. So we're going to look at three planes and find a common point of intersection. And then after that problem, we'll look at an equation of a line and a plane and find the point of intersection between a line and a plane. So let's get started. So here we have three planes. They're described by this system of equations, and we want to determine the coordinate of the point of intersection. All right. So before we ever get started with problems, it can be very useful to see, hey, do I have an efficient approach that can help me solve? And if I look down this middle column, I should see that, hey, I have two positive y's and two negative y's, so I may be able to solve this, I, this system by elimination. If I want to find the point of intersection, I already know that there's a unique solution. So let's write our system. X minus 2y plus 3z is equal to 4. Let's write that z a little bit better so we can see it. And we also have 2x plus y minus z is equal to 2. And then we have 3x plus y minus 2z is equal to 0. Okay? If I add all of these together, I get x plus 2x plus 3x. That's going to be 6x. Right? We already said that we saw this middle column going to give us 0y. But notice by chance in this third column, the z column, we also have that same relationship. So that's nice for us. So plus 0z is equal to 6. So what does that tell us? 6x is equal to 6. So that means that x is equal to 1. Okay. Now let's revisit these two, the second equation and the third equation. Notice that if I take, all right, equation 2, or no, let's do equation 3. If I take equation 3 and I subtract equation 2, what's that result? 3x minus 2x is x, y minus y is 0y, and negative 2z minus negative z is negative z, and then 0 minus 2 is negative 2. So that means that x minus z is equal to negative 2. So therefore, z has to be equal to 3. All right, and so now I know my value for x and I know my value for y, and so I can use any of the equations to determine the value for x and the value for z, excuse me. Then I can use any equation to determine the value of y. So 3 times 1 plus y minus 2 times 3 must be equal to 0. So 3 plus y minus 6 must be equal to 0. So I know that y must be equal to 3. So I have a point, right, and I'll use parentheses for a point. So I have the point 1, 3, 3 as the coordinate of the point of intersection. So I can try solving by elimination. I can use other methods. This happens to be a non-calculator question, so I want to make sure that I can work through that. Okay, so the more practice you get, the more comfortable you're going to feel. All right, so continuing with our intersections. Here in figure 3, we have two visual examples of a line intersecting with a plane. So here's an example through a point P, a directional vector for a line L, and I intersect at point Q. And here's another example that I have a plane, and I have F to N, right? And I happen to be intersecting this one at point P. So it's important to understand the labels of our graphs. This is plane P intersecting at point Q with line L. While this is plane C, right, normal vector N, right, intersected with the line F to N, or the line segment F to N at point P. So the key to understanding intersections between points, between planes and lines is there's a common point of intersection, right? that I have a common point of intersection. So we're going to look at this particular problem. It's going to be calculator active, but I want you to think about how you would solve it without a calculator as well. Okay, so how would you solve this without a calculator as well? Well, the first thing to solve is to get a parametrized form of my line. So if I parametrize my line, x is going to be equal to 2 times my parameter minus 3. Y is going to be equal to 4 times my parameter plus 5. And z is going to be equal to 2/3 times my parameter minus 1. Right, the way that we can think about solving this is by saying each one of these items in Cartesian form has to be equal to my parameter. So I would say 3z plus 3 has to be equal to 2 lambda, right? And then I can go through and say, well, what happens if I divide everything by 3 and then subtract? That's what I have. So these x, y, and z coordinates based on my parameter for my line must work within the equation of my plane. So that means that 5 times 2 lambda minus 3 minus y times 4 lambda plus 5 plus 4 times 2/3 lambda minus 1 must equal 2. If I have my calculator, I can just come over to my equation solver. So I'm going to add an equation, and I have 5 parentheses 2 times my parameter. Let's let the parameter be t minus 3, close parentheses, minus, all right, I don't need the minus y because the y is that 4 lambda plus 5. So minus parentheses 4 times my parameter plus 5, close parentheses, and then plus 4 times the parametrized form of my z coordinate, which would be 2 over 3, right, times my parameter. We'll use t like we said, minus 1, and that needs to be equal to 2. Using my calculator, I can solve the equation, and I see that my parameter is equal to 3. All right, so therefore my point of intersection is going to have an x coordinate of 2 times 3 minus 3, which is 3. I'm going to have a y coordinate of 4 times 3 plus 5, which is going to be 17. And I'm going to have a z coordinate of 2/3 times 3, which is 2 minus 1, which that would be equal to 1. So the common point of intersection, right, is going to be 3, 17, 1. Now, of course, that parameter we used in the parametrized form of our line, we can verify that it works within our plane as well. All right, 5 times 3 minus 17 plus 4 times 1. So that's 15 minus 17 plus 4. That's equal to 2. So we can see that, yes, in fact, that particular point does satisfy my system of equations. So it's just a substitution approach when you have a line intersecting with a plane. All right. The visual can certainly help it out, and so your key is going to be get the parametric form of the line, substitute into the Cartesian form of the plane, solve for the parameter, substitute back to the line, and you'll have your point of intersection. Thank you for your time.